PhD. And so as a mechanical engineer, I became responsible for all the electronics areas, which was unique. And then I became the head of the aircraft department, responsible for all the airplanes in the Israeli Air Force, helicopters, airplanes. And then I became a brigadier general, the head of all the technical stuff under the commander of the Air Force. I retired 15 years ago. I joined Ben Gurion University as a full professor. And in addition to that, I built several startup companies. If there is some time at the end, I'll say a few words about the startup companies. Okay, so one thing that I found through my years in the Israeli Air Force, that we are doing too much maintenance. We are maintaining the F-16 engine every 600 flight hours. We remove the engine. And in the depot, we don't find almost nothing or minor things. And the price for this maintenance is millions of dollars. Removing the engine, installing a new one, the spare parts, the work, everything that is done is a lot of money. And at the end, the people in the depot tell me, hey, we didn't have to remove this engine. We didn't have to remove this engine. And it took me time to understand that asking as engineers if we get an engine and we should remove it according to the OEM, the manufacturer here along that line. When we design it 4 times more and even more. As engineers, we have a lot of conservatism, and the engine could stay all that time. So we lose all that area when we do the overhaul. On the other hand, sometimes we will have a premature failure. We would have failure before the time that we have to inspect, okay? And the reason for that, sometimes the aircraft is maneuvering outside of the envelope. I had the A4 Skyhawk that the airplane crashed and the engine failed because the pilot went outside of the envelope. The temperature of the engine was too high. The blade got longer and touched the outside of the engine, broke it. The engine blew up and the airplane crashed. So it was before the time that we had to inspect it. You cannot find that problem just by doing this conservative maintenance. Sometimes the material that is used is wrong. Sometimes the design is wrong. Sometimes there are problems that, although you spend all these millions of dollars, at the end, you lose the airplane. You have a problem much earlier. Okay, I hope this chart is well understood, because this is something that bothered me all my life in the Israeli Air Force. I felt that I'm spending most of my money. I was the one at the end that allocated the money for the different groups in the Israeli Air Force under my responsibility. And I felt that I'm putting a lot of money in the areas that Boeing, Lockheed, Israeli aircraft industry tell me to put. And at the end, I don't get extra safety. I lose readiness. I lose spare parts. The logistic chain getting longer. And who is winning from that? Who is getting more money as a result of that? Do you know? Do you have any idea? The OEM. The people that told me to remove the engine every 600 flight hours, they are getting more money. It's part of their business case. So that's the reason I couldn't change that with them. So I had to go and change that in the industry with the engineering capability inside the Israeli Air Force. So with that, I came to the idea that we need to go to condition-based maintenance and all these nice words that we are using. I'm happy that a lot of people and the DoD and a lot of organizations are using that today, but it wasn't like that in the early 80s when I felt that problem. I wrote in 94 a paper in Israel which said that we need to go for a different maintenance concept and to go for condition-based maintenance. And in Israel, we developed a system in Israel that was installed on the Apache that collected data from 30 sensors, mainly vibrations. And based on that, we made a decision in the O&I level whether to replace parts or not. And later on, the Army and the Air Force in the United States developed something like that in Honeywell and Sikorsky. And back then, the idea was to track that's the dynamic components of the Apache. We had critical locations, but based on the vibrations, we did kind of analysis, and we had condition indicators. I'll say a few words about these things. And based on that, I was hoping that we could go from the standard maintenance concept to condition-based maintenance. But it was a very good system. It is still being used, but we couldn't go to condition-based maintenance completely. The algorithms weren't robust. We couldn't estimate the severity of the damage. We couldn't do prognostic RUL, meaning the remaining useful life. We couldn't get the remaining useful life. We felt that the sensing wasn't good enough. All the AI algorithms basically failed completely. And we felt that we need more understanding and better algorithms, more robust algorithms. So the system helped us in many cases to find problems, but it didn't let us go to condition-based maintenance, okay? So in my mind, when I retired from the Air Force, I decided to join the university. And I said, once I joined university, I'll try to develop better algorithms and better methods that I didn't have when I needed them. One of the last things that I did in the Israeli Air Force is to sign a contract to buy the F-35. And from our side, we put a lot of pressure on the JPO, the Joint Project Office, and on the Lockheed to get some condition-based maintenance concepts. And they put a lot of algorithms in the airplane, a lot of sensors. But I don't believe that even today they have full condition-based maintenance. The Ali system is, in Israel at least, it's considered to be a very bad system. No, user-friendly algorithms are not as good as they were expected. And also the train industry in Israel are fighting to get condition-based maintenance concept, and maybe I'll say a few words about that. Now, we realize that many areas need predictive maintenance approaches. You can see the energy, the oil and gas, chemicals, metals, mining, and basically everyone, medicine, medical area, everyone needs to understand when to maintain, what to maintain, and you need to improve the readiness of your equipment in order to be more efficient. The DoD, the American DoD came with the CBM Plus. I don't know if you're familiar with that. And they understand that the maintenance is a big burden, and you need to improve the availability and readiness. And in my opinion, it's very critical very critical to save the costs of when you spend the money, you are always limited. And if you put your money on maintenance, you won't put it on other things that sometimes you need more. And even inside the maintenance, it's better to do other things than over-maintain. When you over-maintain, you can cause also some problems. Several years ago, in 2022, I got a Lifetime Achievement prize in the PHM conference. I was very proud about that. And so when I established the lab 15 years ago, I wanted to create an Israeli Excellence Center for Advanced Health Monitoring for machinery. And I said that I wanted to collaborate with as many organizations as possible, from academia, from industry, and so on. And we have a lot of collaborations. The next time I'm going to put one more with Ed. Now, what we wanted to get in this center is basically for every mechanical part, we wanted to get the following. If you have a failure mode, most of the times it will look like that: damage versus time, or versus cycles, or whatever. You have a long time, which is green here, very short, but in life, that's 90% maybe of the component life, where there is no damage. Later on, there is a damage that is growing relatively slow, and then there is a knee. After the knee, it will grow fast. And the key things that we wanted to find is whether there is damage or not. If there is damage, whether it's below the knee or after the knee, and in which component is that, what is the rate of growth, and when should we replace it? When should we treat it? What is the RUL for that component? These are the questions. And even today, I think there are not good solutions. So a lot of questions related to that. Although many companies and many organizations say that they can do diagnostic, which is to assess what is the damage size right now, and prognostics, which is what will be the RUL, for how long can I still use fly with this component. So these are the challenges that we tried to face. And in the lab, we are concentrating on bearings and gears studies. Basically, we started with physical models and experiments. That's what we did for many years in the lab. In the last 6-7 years, we added the data-driven and AI models. And the problem is that when I was in the Israeli Air Force, I spent a lot of money with several companies that were doing AI, but the results were, you couldn't count on that. And there are a lot of problems using AI in vibration analysis for health monitoring. I'll say a few words about that later. So at the beginning, I said no AI people in my lab. In my lab, only physics-based and experimental. You have a model. Okay, you need to validate the model with experiments. And AI guys, they just want to write papers. They don't really want to maintain. That was my understanding. Well, today, it's not so different, but I understand, I think, a little bit more than that. So I'm a little bit easier with them, but still, I think it's very dangerous. I wanted to give you one example of the type of work that we are doing in the lab. This is CH53 swash plate. That's the plate that is located under your helicopter guys. So you should know this is the plate that is located under the rotor head. It controls the angle of attack of the blades. Well, in the Israeli Air Force, we had inside there is a static swash plate and a rotating swash plate. In between, there are bearings, two bearings. And the Israeli Air Force had helicopter flying far from Israel. Suddenly, they felt vibrations. They found an island, they landed. And what they found is that the bearings were broken. They were lucky to land. If they didn't land, they would crash. Now, there's no way to inspect that. If you want to inspect these bearings, you have to remove the blades, you have to remove the rotor head, you need to remove the swash plate, send it to the depot, open that. And if you do all that, it takes you 2 weeks before you can fly again. And you need to do that before every flight after that. So we developed for them algorithms to track the health of these bearings. And the way we did it was like that. We had experiments, started with a toy problem that is similar in the cross section with the swash plate. Then we built a test setup that can load the swash plate you can see on the right. Then we went to a ground run-up station and we ran the tests. So we had a lot of experiments with and without damage in the bearings. In parallel to that, we built a dynamic model. A student did that for his master's. And he validated the model against these experiments. And once he validated the model, we could run many cases and develop indicators that could tell the Israeli Air Force if there is damage or not. And based on that, they are flying the CH-53. So this is an example of the work that is done. Another type of work that we are doing for prognostics, we are running endurance tests. Some of the work we do in the lab, and some of the work is done in AFRL, in the Air Force laboratories in Dayton. We have a collaboration with them. They run, for example, bearings for us in different conditions. From the experiments, we get vibration level. We build a dynamic model. We use finite element, calculate the damage in the bearings. I'll show you how we do that later. We are using ODM. Do you know what is ODM? It's an oil debris monitoring. It's a system that measures the size and the amount of particles in the oil. And we developed for them the algorithm that based on the ODM data, you can calculate what is the damage in a bearing, for example. We have several papers with them about that. And from the finite element, we can calculate the fault propagation model. And based on all of that, we developed RUL estimation models that we are using today. For example, this is a research that we did maybe 14 years ago. We wanted to calculate if there is a spall in bearing, what is the size of the spall? You can see the red area in the model. This is the spall. Spall is a fatigue damage that grows with time. That's the most common failure mode of bearings. And so what we did, we built a model of the real case. And we found from the model how the dynamic behavior that you can see on the right side of the balls inside the bearing. And we understood that when the ball enters the fault, there is one behavior, and when it goes out, there is kind of rattling, and from the frequencies in the different cases, we understood how to find the entrance of every ball to the spall and the exit. And from there, we found what is the damage size in the bearing without open the engine, without open anything, just from the vibrations analysis. And this is the algorithm. I won't go into the details, but it's based on the understanding what would be the dynamic behavior of the bearing in the entrance and in the exit. So this is just an example of how you can develop algorithms like that. This is the test fixture that is used in Wright-Patterson. They are running the tests for us. And we've developed together with them many condition indicators that are very, very accurate, in my opinion. Several of them are based on ODM, the oil debris monitoring. Some of them are using some algorithms that are factoring the varying tones. Some of them are using some energy algorithms. I won't go into the details because we are short with time, but there is a lot of work that can be done with that. This work is related to prognostic, to the damage growth in bearings. We try to understand how the damage grows in the bearings. And we spent several years running endurance tests and studying the literature and coming up with. In the upper level, you can see the crack initiation phase where the cycles cause some fatigue damage and the first piece would leave after that. In the second stage, the damage starts growing, and we wanted to understand how the damage is growing. So all that work was done both experimentally and using finite element models. And we found that the fatigue growth is caused by the ball hitting the corner of the spool after the first piece left. And two different cracks are being developed. Some of them are from the surface, other ones are from below, and they are connected. And then we get another piece leaves. You can see here simulations of the damage. You can see, for example, on the top, the cycles where the first initiation. In the lower one, you can see how the hits of the ball starts growing. I'll take it to different stages. So there is damage growing up and down. And this is in a fast mode. So then another piece leaves, and we have a new spool, longer, and so on. And you can see it in the right lower corner. And based on that, we developed a model that you can use for prognostics. Okay, I won't go into all of that, but we have models like that for gears. I'm short with time, so we have indicators for gears. I want to say a few words about sensing. We realized that accelerometers have also disadvantages. And we understand that we want to be close to the damage. We want to have a signal-to-noise ratio, which is good. And we started using, in addition to accelerometers and measuring temperature, the ODM, FBG, and small, tiny cameras to inspect the health. Let me run quickly. Those of you that are using the FBGs, you're measuring the strain on a fiber optic. And from the change of wavelength, you can calculate what are the strains. And mostly people are using it for measuring strains in structures. We are using to measure the behavior of bearings and gears. And we have several papers where we were able to correlate between the damage sites, different damages, to the strain level and some analysis that we have done. As I'm short with time, I won't go into details, but if someone is interested, we have a lot of modeling. And several years ago, I met a company that makes tiny cameras for medical purposes. And they were selected by NASA to put those sensors in the satellite pipes to check the health of the pipes before refueling the satellite. And then I said, okay, if you can use that in the space technology to assess the health of the components, why can't we do that in aviation? So we lost in the Israeli Air Force an Apache because the push-pull rod that transferred the pedals of the pilot to the tail, controls the tail angle of attack, was disconnected. All these rods which are outside of the airplane are inspected every pre-flight. And the ones that are inside, in order to reach this point that you can see in the red mark, to see this connection, you need to remove the pilot seats, you need to remove the fuel cell. It's a long, long way to inspect that, and you cannot inspect that. So what we did with that company, we installed those tiny cameras inside that bay. You can see a picture taken, and we connected it to a plug. And now the technicians they connect to the plug, and they can see in the iPad that the integrity, they can check for the integrity of the system. So with this concept, you can inspect areas which are not related to rotation, areas like landing gears, like many other areas. You fly with the camera, you don't need to do anything, and you can inspect it. But then I realized that if you have a good picture, good image, you don't need the technician. You can just put a computer on board and develop algorithms that will check for corrosion, for the safety wire that is there, the solid parts should remain solid. And from that point, the company changed direction into investment. And there are, for example, application for landing gear. You can check if there is leakage in the landing gear. You can check from the trajectory of the landing gear that the bearings in the different locations are not wearing out. We lost an F-16 in the Israeli Air Force because during landing, the locking system jumped out, the main landing gear collapsed, and the airplane turned over. The pilots were lucky enough to eject in the last minute. Today, you can eject on 0-0. On the ground, you can eject safely. So they were lucky. But we lost an airplane. And the bearings were completely worn out. So if you put two cameras, make the trajectory, analyze the trajectory, you can do damage assessment, you can do forecast what would be the best time to maintain this area. This is, for example, for a UAV. We are installing now in most of the Israeli UAVs, tiny cameras connected to computer, and areas like belt integrity, filters, throttle. Many inspections are done with the system by itself with no technician around. We started saying that we don't have a pilot. The pilot is remoted, and you don't need a technician as well. The airplane can inspect itself, let you know that everything is okay and is ready for the next mission. So you improve the readiness. You don't have to open panels. You don't have to, and the camera is not tired. Can do the work at middle of the night. When I was the head of the maintenance unit, when the helicopters used to land, always they land at midnight or very late. and then you send the technicians to inspect the airplanes for the morning flights, and then you are not sure that they can do the work as accurate as needed. They are tired. Camera doesn't get tired, and the probability of detection is much better. So we have a lot of applications today. Let me jump. I'll say a few words about AI. So deep learning for fault diagnosis of rotating machinery using vibration is kind of used to be a buzzword, and there were several waves of deep. I'm not an expert, not in deep learning. I'm not an expert in that area. I'm working with experts, but I remember where you couldn't get a grant if you didn't write AI in your grant, and in the picture classification and speech recognition, there were a lot of revolutions, and they developed features to identify what you have in a picture and so on. And it looked like a very promising tool, not only for these areas, but also for analysis of the vibrations that we measure with accelerometers for health monitoring. And there are thousands, maybe millions of papers written about using different algorithms and different methods using AI for assessing the health of machines. And the real problem, in my opinion, is one of the problems is in the critical locations. You have very, very, very few, even sometimes zero data about failures in critical locations. For example, in the F-35, as far as I heard, they are planning to develop the algorithms after they have 200,000 flight hours. That's what I heard. Now, I hope in the first 200,000 flight hours, they won't have too many failures. They won't lose thousands of airplanes because of damage. So the database that they will be using is probably few or zero short learning. And the problem is to move from experiments to the real life. You cannot do that directly. Transferring different conditions, different machines. Even if you're using the same bearing on the same machine several times, you'll get different data. And you need a lot of labeled data in order to train your system, in order to use it. So in my opinion, no one is using for critical locations only AI-based algorithms to maintain its fleet. That's what I think. Of course, I didn't visit all the air forces and all the users, but those that I visited, they are not doing that. And one challenge that we realized, and we are trying to solve it, is to transfer in identical machine from different operating conditions, meaning I train my data on certain conditions and I move to other conditions. And the other one is to transfer from different machines, meaning I learn on one machine and I go to another one. If we solve this, probably we could develop algorithms training on the lab, in the lab, and then use it in the airplane. But it's not solved today. There are a lot of research right now being done in this area. And we did a literature survey, and we found that none of those studies are being used in real life. It's very, very easy, I can tell you, to write a paper about that. If I have data, I can train the data, change several parameters, and on the same machine, same conditions, I can identify whatever you want. I've done it very easily. And us in the academia, we need papers, so we can write many papers. So this is a great area. You can develop very fast papers. You can get promoted. That's an industry that feeds itself. But if you are responsible for flying airplane, for maintaining airplane, this is very dangerous. You cannot do that. And what we are trying to do in the lab, we are trying to use experimental results and simulation using the models that I described before. And based on the combination, the hybrid method, we are trying to check and to develop methods that will work in real systems in real life. And so this is just a teaser on that area. I hope to have a collaboration with your center related to that, because I'm very anxious to come up with a solution for that problem. I'll say a few words about digital twin and then I'll sum up. I have to sum up on time. So the concept of digital twin looks like a buzzword. When I first saw it 10 years ago, I said, that's another buzzword that came and will go. Now, with the years, I found that you can do things with that. If you have a good model, and if you have data and sensors on board, you can get the data from your individual airplane or individual asset, put it into the twin, and measure and check the health or check other things. And you can use it for many, many things. Let me just show you the results of a project that we did with the train industry in Israel. What we did, we took 5 critical components and we developed a twin for those components. We trained the system. And once we had algorithms that can identify damage in different locations, we use that, they use that, they measure the data, they put it through the algorithms, and if something is wrong, they go and check the area. If they find something, they fix it. If they don't find anything, they understand that the model is not good enough, and they go back to the above system and they improve the model. So this is a learning process where they get better and better, and it saves for them a lot of man-hour to remove parts just because the OEM told them to remove. Okay, so just to sum up, I talked about machinery condition-based maintenance. I think that even today it's a big challenge. We can save a lot of money and improve readiness, improve safety, if we have a good solution for that. We need to improve sensing. We are working on several directions. I know that others are working in different directions, and I'm sure that in 20 years, it will be like our body. If something is wrong in the heart, you will feel it through pains or through sensors that you put outside. You can do AKG. You don't take out your heart every 600 flight hours and you inspect it. You do that only if all the sensing methods tell you that you need to do something. The engine is like that. The transmission in the helicopter is exactly like that. AI approaches, okay, I suffered a lot from trying to use it in the Israeli Air Force. There is a big challenge there, but I think we can solve it. The academia, the community can solve it. And the last thing is the digital twin. I didn't have time to talk and to show you more research about that, but I think there is a lot of potential in using these concepts in engineering. That's it. Thank you. Do you have any questions?
Yeah, very, very nice.
Thank
Toby,
you.
thank you.
Thank you.
Did not disappoint at all. Any questions from the room? Yes, Hank.
So health monitoring can reduce the amount of maintenance that's required, but are the sensors that monitor the systems, do the sensors require maintenance? Like if you have a camera or something, like you don't want your camera to break or some type of like accelerometer or something like. You must have to monitor the sensing systems as well.
Excellent. Yeah, of course, the camera and the accelerometer is being checked through the algorithms that you are using. So if there's the quality of the picture is going down, or the camera deteriorates, or you don't get a picture, then the system will tell you immediately that something is wrong, and you would have to replace it. But you have to make sure that the MTBF, the mean time between failures, will be large enough that it won't happen shorter than the component. And the other thing, you have to make sure that a failure of the sensor of your inspection device won't cause a failure to the system. That's another thing that the tracking, the sensing system can fail, but you can continue operate your machine. Okay.
How does the oil monitoring work, especially if you put it inside a bearing?
Okay, you have circulation of the oil. So the oil goes into the bearing and goes out. You force a stream. And then from the stream, you measure the change of magnetic field. There are different methods, by the way. You can use there are optical devices that take through the oil pictures, or we are using electromagnetic sensor. By the way, this sensor is installed on the F-35. And from the change of magnetic field, they can calculate how many particles are there and what is the distribution of size. I have a lot of data about that, and we published a paper that relates the data to the damage size. So now you can go from the data that you get to maintenance, make a decision when to maintain.
Good question for a aeroacoustics guy. That's not bad.
By the way, acoustics and vibrations are very similar. The analysis, if you're using a microphone that measures the vibrations, you're doing a similar analysis to what we are doing in measuring and analysis of the vibrations in the material itself.
After you remove a component, do you do tests on it? Like, let's say, a helicopter, like the OEM says, move back for 6 hours. So you do that, you remove it. But you don't know, right? Like, in the ideal world, you remove it just before the meeting. But how do you know, right? Obviously, it's hard to know where it is.
In the field, you don't do research. You are.
Yeah, of course. Yeah, exactly.
But you send the part to the shop, to the overall area.
Yeah.
In the overall area, a lot of components, you inspect them. And if there is no damage, you put it back and you continue using it. The same thing with structures. In the structure, you don't throw the wing because the wing of or a flap or whatever because it finished 2,000 flight hours. You inspect it and you return. You have a depot level, and then you send it back to the field. Now, the inspection takes a lot of time. The inspection can introduce damage. The inspection requires some spare parts because some of the screws, some of the O-rings, a lot of them you need to replace.
Yes.
And the engine blades, for example, they give you a certain time and that's it. You cannot use it again.
Yeah.
And with that, you're paying millions of dollars. A lot of the maintenance takes a lot of the money that we pay for tickets to fly the 787, for example. And it shouldn't be like that. We should, like our heart, we shouldn't remove the components just because the OEM told us. God didn't tell us to take the heart just because he needs more hearts up there.
He has a bigger bank account.
I guess so, right?
Any,
Sometimes I don't understand these decisions, but
Everybody, some question online?
okay, how do we do that?
Let's see, chat, right?
He has his hand raised. He unmuted.
Maybe we can open the microphone so.
Oh, I can have Mr. Brown. Sure.
Oh, do you know how to do that, Kelly? To open, so Roland plots?
Hi, can you hear me?
Yeah, you just have to put your sound on over there.
Oh,
Okay, let's put the sound. I'll do that.
Because we'll get a lot of feedback if I find one.
Can you hear me? Can you hear me now?
That's the.
let's see, we'll try this. Now we'll read the chat, but
Can you hear me?
sound is on. He's unmuted.
Hello.
Can you put your?
1, 2, 3.
If
Can
you
you hear
mute
me?
yourself, then I can, yes.
Can you hear me now? Are you able to hear me?
Yes, we can.
Oh, great. Thanks so much for this very insightful talk. I'm sitting here in South Germany, so I'm getting ready for my dinner as well. So I was wondering, with your experience and your studies so far for AI applications, do you see from today's point of view any, I would say, like natural barriers of any AI or machine learning approach that will actually never really fetch or get the idea of what kind of damage or so we are looking at? Or is it just a matter of time that these algorithms become so good that they do that? Or do you see any kind of a Pareto front that says that there is just a natural limit in it, and we cannot and we will not avoid any testing and mathematical modeling?
Can you hear me?
Yes, I can.
Okay. Now I'm mute. So, first of all, I have to say I'm not an expert in the AI area. So take my words with the limitations. But in my opinion, the first problem is that we cannot transfer from one system to another system, or from one condition to another one. I think it's doable. There are tools that can help us transfer the learning. And I know that in other areas they did it, and we are learning that. Now, in addition to that, I believe that the sensing is getting better. For example, with the tiny cameras, the computer vision analysis let us see everything. Everything that you can see, the camera can see, and the technician or the automatic algorithm will give solution. But if we are talking only on vibrations, there is still a long way to go, but I'm sure that it's solvable. I'm sure that we will be able to learn in a test bench and understand what to do in the real life. But there is work to be done. That's my opinion. I hope I answered the question.
Yeah, I mean, we were there before. I remember like 10, 15 years ago or so, when the automotive industry thought they could get rid of any experimental testing, and they were just doing everything on the computer. But then, as I found out, especially with one brand here in my country, with Opel from General Motors back then, that they had huge issues avoiding doing any tests. So probably even with the most sophisticated AI problem, we will never, we will always have experimental testing. Otherwise,
that is another question. Now we are asking, do we need experiments? I think every time that we do something new, we would need experiments, at least to validate the model. Because always in the models, you make assumptions. You neglect certain deformations, you neglect certain forces, you neglect friction or whatever. And sometimes that became very important. So I believe that always when we do something new, we would need experiments. But I try to answer whether we could go from the experiments using AI to the real life. I talked about a little bit different area, but I agree with you that experiments, I cannot see that only modeling is enough in safety critical areas, in critical locations.
thank you very much. Very, very interesting talk. Thank you.
Roland, are you in your DLR? Hey, yeah.
Going to dinner.
Where are you
No,
located?
I'm still here. Was it a question to me?
Yes, where are you located, Roland?
Oh, sorry, I have a bad cold. Just mute me.
It's probably 5 hours behind, in front of us.
Where am I located? I'm in the Nuremberg area right now.
So you work for DLR? I forget. Airbus?
Excuse me once again, what was the question?
Who do you work for?
Oh, okay. I'm at the Deggendorf Institute of Technology. So this is about 1 hour east of Munich. But I'm not there, but I'm on in a satellite location. But that's my home university, the Deggendorf Institute of Technology. It is a university of applied sciences. So we have that in Germany. You don't have that in
Welcome to Penn State University.
Thank you so much. Oh, I know that already. I did during the pandemic. I was doing a sabbatical in the architectural engineering department, and so the first 6 weeks were without pandemic, and then I joined you within the pandemic.
The rest was at home.
Yeah.
I have to talk to you about architectural acoustics, actually. We have an issue to solve in our new building. So I'll reach out.
Okay. Well, I'm actually a mechanical engineer. So I was at the architectural department just because I knew the department head back then. So
all right. Well, if you know that stuff, we'll talk.
Okay.
Any other questions? Let's see.
Sure.
I think we're good online.
People need to eat.
Okay, well, if that's it, let's thank the speaker one more time. Very nice. And if you're here, we have about 10 different lunches that Kelly was able to bring for us. So please, get you through lunch hour. Enjoy the Oktoberfest, Roland, and we'll speak to everybody next time.
Thank you very much.
All right. Thank you. Thanks a lot. Bye-bye.